Welcome back to Battleship Systems. Naval firepower can never do its job without something to bring order to the rain of fire. Today we cover the basic science behind aiming the battleship's guns. Please check the errata page in the description. Before the 19th and 20th centuries, you would have to swing your ship alongside the enemy so the guns are pointing at the target. The guns were so inaccurate it would almost be a miracle if a hit was scored. Not to mention the maximum range was only 1,000 yards. These early guns had such a wide dispersion that it didn't matter where you pointed them. The fall of shot would always be arbitrary. Later on, the guns were rifled in order to give the projectiles a spin as they left the barrel. This stabilized the projectiles and tremendously improved accuracy. Guns are aimed by sights. The early sights were telescopes mounted on or perpendicular to the gun bore, but newer guns could shoot further than you could see from their position near the waterline. Eventually, a station high up in the ship's structure was created to house these sights, which was called the director. However, it was soon noticed that even when the guns matched the director's train and elevation, the projectiles were still not hitting the target. There's a number of reasons for this, and fire control is the science behind aiming your guns to compensate for these factors. One of the biggest forces you'll have to accommodate for is gravity. From the second a projectile leaves the gun, gravity will force the projectile closer to the center of the Earth. To remedy this, you have to fire your projectile at an upward angle and give it a trajectory that will fall on the target with the aid of gravity. Gravity is the whole reason the guns of a battleship elevate. A fired projectile's trajectory will look something like this. Where the projectile is launched at an angle, it will also fall at an angle. Since gravity remains constant, we can accurately predict the range that a projectile will travel and fall based on gun elevation. This information comes from a range table, one of the most critical elements of fire control. Let's look at a range table for a 16-inch 50 caliber gun installed on an Iowa-class battleship. This is for the 2,700-pound Mark VI projectiles, firing at a speed of 2,500 feet per second. The first column is the range of the target in yards. The second column is where we find the degrees and minutes of gun elevation for this range. The other columns show path variations that can be caused by different conditions encountered when the projectile is in the air or during the time of flight. Navy range tables are made at the U.S. Naval Proving Grounds in Dahlgren, Virginia. This involves firing an actual 16-inch gun many times, then plotting where the projectiles fall in the Potomac. They measure initial velocity by magnetizing the projectiles and setting up two velocity coils for the projectiles to pass through when fired. If you remember back to Basics of Electricity 2, when a magnetic force moves toward a coil, it induces a voltage. By examining the times of the two voltages on the oscillograph, you can determine the speed. Let's make our own range table. This metal ball launcher fires at about 7 feet per second. Let's try it at a few different angles and see how far the ball falls. So we're going to start off with 15 degrees elevation. Ready, set, fire. So our distance to the point of impact is about 25 inches. We'll now try 25 degrees. Ready, set, fire. The distance from the point of impact is about 36 inches. Now 30 degrees. Ready, set, fire. That's about 38.5 inches from the point of impact. And now for 45 degrees. Ready, set, fire. That's about 41 inches from the point of impact. Just for fun, let's do 55 degrees. Ready, set, fire. This one's only about 32 inches from the point of impact. Now I'm going to try to hit this target with this projectile. Notice our target is no longer in line with our gun. So we're going to have to train our turret to point to the target. Now we know the range to the target is 36 inches. Now if you look back at our range table, 36 inches corresponds with an elevation of 25 degrees. So let's set the elevation to 25 degrees and see if we can hit the target. Ready, set, fire. Now obviously during battle we can't ask the target to hold a measuring tape to find the actual distance. There are rangefinders and radars in the director that can find the present range automatically. It's also important to note that the values in a range table don't necessarily represent realistic firing conditions. One reason for that is after a gun is fired, the projectile will have to move the air out of its path as it moves throughout its trajectory. Earth's atmosphere is constantly changing, and with that, so is the air's density. Range tables are presented in what is called standard surface density. This is always 59 degrees Fahrenheit and a barometric pressure of 29.53 inches. If it gets colder or the barometer rises, the projectile will encounter more resistance and fall short. Range tables have a nomogram to help us determine the air in range based on atmospheric conditions. Let's say the temperature is 85 degrees. The barometer shows 28.4 inches. We draw a line between these 2 points. Then we draw a line intersecting where our line crosses the support line D and the range to the target. So if the range is 25,000 yards, our line would look like this. This tells us that our air will be plus 420 yards. In other words, the projectile will land over the target. We can see the nomogram was based on standard density by intersecting those values on the pressure and temperature scales. Lines intersecting most ranges from here will result in zero error. Another reason range tables can't be taken at face value is they represent what would happen if there is no wind. Wind can affect a projectile's path during its flight through the air. Now this doesn't mean that Dahlgren always waits for a perfectly windless 59 degrees day to do their tests. Mathematicians are able to recompute these values and present them as if the atmosphere was always at standard density. The last condition that we will cover today that causes errors is a direct result of gun rifling. This causes what is known as drift. Since the projectile is rotating in a clockwise direction as it leaves the gun, it tends to behave like a gyroscope. When the projectile is in the upward trajectory, this action is negligible since its spinning axis is in line with the trajectory. But as the trajectory curves downward, the air resistance pushes up on the projectile's nose and causes a precession to the right. That means when you fire a projectile, it will always move to the right. To complicate matters even more, we have to compensate for the fact that the ship and the target are constantly moving. These factors will have magnitude and direction. To determine the impact on our line of sight or projectile trajectory, we create what is called a vector diagram. From these vectors, we can create our ballistic correction. We're going to do an example main battery fire control problem, but before we can start on our ballistic corrections, we need to determine how much the movement of the ship and the movement of a target will throw us off. What I mean by that is we need to determine how much the rate is in and across the line of sight for both the target and the ship. And the way we do that is with something called a line of sight diagram. So we have our target here and our ship gun here. Then we just shoot across the line of sight. Wouldn't that be nice? But no, the target is moving. Now you guys know what a bearing is, right? From the bow of the ship, clockwise, 0 to 360 degrees. What we need to determine is what the bearing of us is in relation to the target. In other words, if the target was looking at us, what would their bearing be? Now, right now, if we look at the target, we can see that the present range, or R, is 10,000 yards. And that also means we're going to be using the 10,000 row of our range table for this entire exercise. But what is our target angle? Now, if we look at the ship from the telescopes and our directors, or from our guns for that matter, although 10,000 yards is pretty far to see from down at the guns, regardless, we can see the starboard side of the ship and a little bit aft. So if we only saw the starboard side of the ship, it would be 90 degrees, since that's their bearing. But since we could see a little aft, we're going to make this estimated it to be 100 degrees. And of course, we might be able to get accurate information from the Combat Information Center, since that's their job. But anyway, looking at our target, they're moving away at an angle of 100 degrees. So we're going to draw a line here for their movement. In this area here, the angle is 100 degrees. Now we need to determine how fast they're moving, which is this component here. Now again, this information could probably come from the Combat Information Center, CIC, and they tell us that the target ship speed is 18 knots. So label that 18. Now what we need to do is break this down, this vectorial movement. How much does it affect us in and across the line of sight? Now, if you look at this drawing I made here, it looks kind of like a right triangle. Now, from somebody who's flunked out of calculus in college, I do remember that a right triangle, if you know the angle in one of the sides, you can use trigonometry to figure out the length of the other sides. So let's do that. Now this angle inside here is going to be 80 degrees. Since 180 subtract 80 is 100, we're left with 80 in there. So we want to find the length of that side. So that's going to be 18 times the sine of 80 degrees. That's going to be 17.7. Now for this side, that's going to be 18 times the cosine of 80 degrees, which is 3.1. So what does that mean? That means that our target is moving to the right across the line of sight by 17.7 knots, and it's moving away from the target by 3.1 knots. Now take a look at this angle here. If we shoot off the range table as it is, the target is moving. Our target is going to land short because it's back here, and it's going to land to the left. So we call that a short left correction. So now we need to do the same for our gun or for our ship. Now the angle is going to be the line of sight in relation to the bow of the ship. So when we look at the target, it's going to have a relative bearing, a B sub r, of 320 degrees. So that means if our ship is moving and we look at bearing 320, we see our target. So we have to make sure that the angle of the line of sight is at 320. If we want to know the degrees of this angle, we can do 360 minus 320. And that will be 40 degrees. So this angle here is 40 degrees. Now we need to know the rate this vector is moving. Well, that's very easy. That's knots. We can determine that from the pedometer. So we'll say the speed S sub O is 20 knots. Now we need to know the impact in and across the line of sight that our ship movement is causing. So that'll be 20 times the sine of 40, which is 12.9. And this side will be 20 times the cosine of 40, which is 15.3. Now, what does the ship's movement have to do with the movement of the projectile? Well, the ship's movement will always be a part of that projectile even after it leaves the gun, to a certain extent. So even if the projectile is sitting in the barrel stationary, the projectile is moving because the ship is moving. So we need to determine how that's going to affect our shot. So if the ship is moving to the right and towards the target at the present range, we would say that the target is going to move over and to the right. So we'll call this one over right. Now, what's between the ship and the target? It's wind. My least favorite part of the calculation. Now, there's 3 types of wind in fire control. There's apparent wind, true wind, and ballistic wind. Now, obviously, there's wind at sea, but there could be 2 causes for that wind. One could be meteorologically, and the other could be the fact that your ship is moving through the wind. So just as a target moves, that wind is going to blow against you, whether it's naturally occurring or because you're moving. Now, ships have devices that can measure the wind. So if the ship is standing still, that will give you the true wind. If the ship is moving, then the reading you get is called apparent wind. And apparent wind is a vectorial sum of the true wind and the reverse of your ship's motion. For this fire control problem, we're going to need true wind. Now, if we look at our wind direction and intensity indicators and plot, we show that the wind is blowing towards ship's bearing 154.5 at a speed of 23.1 knots. Let's draw that vector. Now this is relative to the bow of the ship, and this is a line of sight diagram. So we need to adjust our vector so it points to the target. And the way we do that is by adding the angle from the bow of our ship to the line of sight to our wind angle. So that gives us (194.5 degrees). And the magnitude remains the same. Now this angle is 14.5 degrees. and we could use trigonometry to determine the rest. So the range wind is going to be 22.4, and the crosswind will be 5.8. This is our apparent wind vector. Now to get our true wind vector, we simply take our apparent wind vector and add the reverse of our ship's movement vector. So 22.4 minus 15.3 is 7.1. And 5.8 minus 12.9 is negative 7.1. So that would look like this. And notice this is a right triangle, but it's also an isosceles right triangle. So we know that this angle is going to be 45 degrees. Now we can use the Pythagorean theorem to fill in the hypotenuse, or the magnitude, and that ends up being 10 knots. So this is our true wind vector. Let's add that to the line of sight diagram. So not a lot of magnitude. You should also be aware that this is only the true wind at the ship, and it doesn't reflect the wind at every altitude the projectile will travel. And the longer the projectile remains airborne, the more of an effect it will have. Our maximum ordinate is only 703 feet, which isn't very high. If we were shooting near maximum range, we would have to send up a weather balloon and watch how it moves at various elevations. We would then take these vectors and compute what is called a weighted ballistic wind. Ballistic wind is a fake wind that accounts for all the movement of the balloon. But ain't nobody got time for that. We're being shot at. We're going to have to use true wind. Now this is tricky. The wind is always in contact with our projectile. If the wind is moving toward us and to the right, that's going to push our projectile toward us and to the right. So we're going to call this vector a short right. That's a lot of errors to keep track of, and we haven't even started on our initial velocity corrections yet. There's a link in the description of this video to the worksheet if you want to follow along at home. Now let's find out how much this air is going to slow down our projectile. And for that, we're going to need the temperature and the barometric pressure reading. It's really cold outside, so we'll say the temperature is 20 degrees Fahrenheit and a barometric pressure of 29.9 inches. So intersect these two values on the nomogram. Then intersect a new line with the range, and we get our air of negative 100 yards. That means our projectile will fall short 100 yards due to the air's density. Guns don't last forever. As a matter of fact, every time you fire a 16-inch gun, it will erode the inside of the gun bore. That enlarged bore means that there will be less pressure behind the projectile when firing, and a decreased initial velocity. But we can account for that. We can measure that the inside of the gun bore has grown by 0.2 inches. And the range table includes a graph that shows us this enlargement will cause an initial velocity loss of 60 feet per second. You may be surprised to know that the temperature of the powder charge affects the initial velocity. The range table standard conditions have the powder at 90 degrees Fahrenheit. For every degree colder than that will result in a loss of 2 feet per second. If you remember back to our video on magazine cooling systems, we have to keep the temperature of the powder below 90 degrees Fahrenheit to keep it from decomposing. So let's say the powder is 88 degrees, initial velocity loss of 4 feet per second. So we add that up and get our total initial velocity loss. Now we subtract that from the norm. And we get our total initial velocity. I'm curious, those of you who do long-range shooting, do you see any similarities between battleship fire control? Let me know in the comment section below, and don't forget to like and subscribe. In the next episode, we'll talk about sight angle and deflection angle so we can correct our line of fire. We'll also go over some other factors we have to account for when firing major caliber guns. We love our battleships. In lieu of donations to me, please consider donating to a battleship museum like the Battleship Wisconsin. There's a link in the description that'll bring you to the Nauticus Foundation website where you can donate to the nonprofit organization. Don't forget to put Battleship Wisconsin in the comments of your donation so your money will go to the ship. Thanks for watching.